there is going to be an investment of $500 billion in the US, focusing on building out more AI centers and AI parks, basically. Now, here's the dilemma, and hopefully Scott can shed some light on it. AI data centers, AI factories need energy, but where we consume the energy and where we generate the energy, those are two different locations usually, unless you want to put a small nuclear reactor next to each and every AI data center. So what is being done to, and also transporting energy over long lines, of course, leads to a lot of energy loss. So what's being done to develop techniques or solutions, technologies to facilitate the transmission from energy from, let's say, a wave generation onto a data center some 1,000 miles away. Scott, any feedback, any comments?
Yeah, definitely. So a couple things on the scale of data centers. Let's start with that for a second. So today, a large data center is somewhere around 100, 200 megawatts in scale and size. These are large infrastructure assets, and you can put them pretty much anywhere on a grid that's not already at complete capacity and with not extreme amounts of trouble. Certainly, there's interconnection requirements that you need to go through. Certainly, there's an increase in capacity factor that the existing power generators on that grid are going to have to step up, and the balance of how the power is going to be produced will be impacted by something of that scale. Now, regular, medium size or small data center, 5 megawatts, 10, 15, 20 megawatts, becomes a much less burden. And this is typically what we're seeing being developed and have been developed over the last decade or 2 decades as we begin to build out I think there's 8,500 data centers globally. But what we're seeing today are with the massive growth in AI processing requirements and the advantages of having super large compute facilities, is we're seeing data centers today at gigawatt scales. So a tenfold increase in the scale of that facility. Now, a gigawatt of power generation requirement, this is an entire new power plant required just to power that single asset itself. Now, a data center doesn't operate at 100% capacity all the time, depending on what it's doing, somewhere between 40 and 60, 80% capacity factor are these ranges, but also makes this quite difficult from a grid infrastructure and power planning setup and systems. So the scale is a really important thing to understand when planning a power grid, when planning where you can site and locate a project, where you can generate that power in the most advantageous and lowest cost location, but then also where you can locate a data center which has the ability to deal with the cooling, because a gigawatt scale data center produces a gigawatt of heat every hour. And so, you've got a huge amount of heat that you need to displace. And so the factors that where you look to site and where you look to locate these projects, both from a generation standpoint, but then also a data center operation standpoint, these play into really critical components. And you're right to say that necessarily where we're going to generate that power, or where the opportunity to generate that power is, and where that data center is located, are not always directly correlated. We do have technologies that can move power across very long distances. This is the AC versus DC battle that went on, and where you've got high voltage direct current transmission lines that can move power thousands of kilometers, and we have plenty of great examples of that happening and being implemented. And alternating current or regular power infrastructure lines that we've developed cannot compete on a long-term transmission. You get compounding losses over that line, versus a high voltage DC lines can move power with very minimal losses across thousands of kilometers. But you can't extract power out halfway through that process. So it's really a point-to-point transmission type of type of system. And so what we're seeing, certainly across the United States, is we're seeing a massive growth in the number of HVDC line development. These take a decade and a half to develop and build. Doing large power infrastructure transmission projects are incredibly take a very long time to do. Going across borders, which we have examples of, also runs into other challenges in borders, whether that's Canada, US, Mexico, or any other country, or even across state lines, also becomes major challenges and can create super big hiccups through these projects. So this is part of the planning and infrastructure that you go through when you're trying to develop or site a project. But there's a bunch of really cool opportunities that are emerging now, where we're seeing the ability to do underground tunneling in much more efficient pathways and speeds that otherwise would have been impossible to do. And I believe we're gonna start to see the power transmission lines going more underground because of some of these technology advances and advancements, and the ability to be able to permit and develop a transmission line underneath state or national highways. This is going to really dramatically change opportunities. But these are when you're looking to develop a new facility, it's something that's super critical to plan. One other thing I want to touch on is just on the developing small modular reactor systems. This is going to be great, and we are really going to transform our ability as a species to be able to generate power in many more locations. But building a nuclear facility, whether it's a small modular reactor or a standard nuclear facility, this still takes a significant amount of time to get through siting and location and planning and setbacks. And like, you're not just going to see a small modular reactor pop up in your backyard community down the street in a small light commercial industrial park. These take a significant amount of work and risk and resources in order to have and build these facilities. It will dramatically change and shorten the time frame for developing and building power infrastructure, but don't expect this to pop up in a day or a month or even a couple of years. These will still take 6, 7 years, 10 years to plan the sites and facilities. Just going to be a much lower scale, and we're going to be able to do many more of them, and we're going to have consistency because the systems will be consistent. The manufacturing of the assets will be consistent, versus today, most nuclear power facilities are very bespoke to the site and location. And so we'll get a great deal of standardization, which will speed that up, but not in the context of how fast AI data centers are being built and developed, where they're not even waiting for interconnection for a regular to a regular grid. They're putting diesel generators on site to power data centers. Like I believe XAI's system has natural gas turbine systems that they have just in containers. So that's the speed that we're seeing some of the development happen, which is incompatible with nuclear power generation.
And thank you, Scott. I'm glad that you mentioned HVDC. Nikola Tesla would be proud. I think we need to look into his other ideas that he launched over about 100 years ago.